Welcome back. And this session we start with Haas telling us about how to compile Cactus on a brand new.
Yeah, we'll see. Thank you. So thanks for having me. Hopefully those remote can hear me, both whether I'm standing here or whether I'm at the lectern. I'll try to speak up a bit and we'll see how that works. So I'm probably going to do a little bit of a different thing than what I had in the actual description. I think mostly what this will be a guided tour of how the Cactus build system works and what goes on once you build an executable. So this is a Jupyter notebook that actually is present in your home directory on the Perl server. So I hope everything actually works in there. Mostly just follow along and sing along, but you can have to give it a try. The file name is Cactus build system .ind, and you should be able to open that one. And there's a couple of cells that are actually executable. Not that they do a whole lot, but they actually in the end manage to compile and build a Cactus executable and the utilities. Okay. So I guess all of you are in one form or the other somebody who has used Cactus and the executable that comes out of it, maybe with the exception of
Hi, Roland. I'm Kyle.
Kyle, sorry. Okay, I was saying Kelly, no, not Kelly. Kelly's the wrong. Okay, Kyle. Right. But most of you will have used SimFactory because that's what we officially advertise. The old timers feature here and possibly Zach and Steve online almost certainly have used other systems as well, but they can run the SimFactory. So what I want to do here is I want to show what goes on underneath the hood. So that not so much that I say this is what you should do, but if you get an error message out of SimFactory and you don't know what the heck this thing is doing, this may be helpful because you understand what is it actually doing underneath, and you might be able to do it yourself. So principle, Cactus uses a actually standard make-based build system. It uses autoconf for configurations. Normally it doesn't matter to the thorns, but yes, it's there. That's where you see the configure output. And it does so to support various clusters. Usually on different clusters, you might have to use a different compiler. So what we do is we define makefile variables that are used. So we don't write GCC for the compiler, we write $CC and $CXX. That's very much standard. That's what you will find in pretty much all assembly codes. It's also what you would find in autoconf. So if you compile a application software via configure, make, install on your Linux system, this is the same thing. So this is all fairly standard and is well understood. Now, first way of making such a system portable to different clusters is just, okay, I want to support 6 clusters. I'm going to write 6 makefile fragments that define these various variables. Then when you compile on the Delta cluster at NCSA, for example, you replace a makefile fragment, this machine.def, with the proper one for this particular cluster. You compile and you're good. That's one way of doing it, and that's what a lot of codes will do initially. In the toolkit, we have Simulation Factory, which contains a collection of these makefile fragments effectively, plus bits and pieces that then set up things like modules, and also having information about how to submit a job to the queuing system of the cluster. And that's really just a database and things to make things easier for you. If it works, it's all great. If it doesn't work, then usually you don't find out what's going on. So here, I'm going to show you what these options actually look like, how they're used, and what the individual steps of compiling Cactus look like. Okay. I didn't touch anything. Right. Let's see. I guess this is still readable to everyone and it's wide enough. All right, so introduction here. All right. we can see how to use the tutorial. This would be mostly if you want to read through it after. But one thing that we have to understand is how Cactus actually organizes its files and how the directory structure of Cactus looks like. So Cactus consists of a collection of modules called thorns that are representing different physics components, or also the mesh refinement driver, carpet, or I/O. There's only one level of organization that Cactus allows. You can have thorns that are arranged in arrangements, and that's about it. So you can have multiple arrangements, which can have multiple thorns in there, but they can't be arrangements of arrangements. So there's a limit on how much you can nest this thing. Basically, to make your life a little bit easier. Each thorn has a couple of files that describe to the Cactus build system what the thorn does. Some degree from probably least familiar to maybe more familiar. There are 4 CCL files. CCL stands for Cactus Configuration Language. It's some sort of a domain-specific language that was meant to describe these things. It's not the same language in all the files. That's what we have. So configuration.ccl describes basically compile time capabilities of the thorn to the build system and how it could be connected to other thorns. Often you won't need that. One that you almost certainly will need, and that I think you also saw in the how to write a thorn example that Maxwell gave, is interface.ccl, which describes to Cactus the variables that the thorn uses, and that it makes also available to others. So that's kind of data. And there is param.ccl, which describes to the build system and the runtime system all the runtime parameters that the thorn supports. Everything that you can use to tweak what it does. That might be resolution, it might be the initial data file that you want to read. Everything that the user can specify at runtime. And then final one is called schedule.ccl. Then where you put all the statements about which routine you want to run where you can also define your own schedule groups, which are collections of schedule routines that make it more easy to call the same routines in multiple places. But these are the 4 files that describe the build system to some degree. There's another one that often looks very straightforward. That's called code.defen, which tells the build system only which files to actually compile. If you look at a traditional make system, then what you actually do to make describe what you want, the output, and what you need to get that output. You say, I want that object file. To get this object file, I need to have that source file. Then you have a recipe that says, that source file, produce the object file. That's the traditional way. It's basically, if you want to, it's task-based or dependency tracking, whatever else, but it's kind of backwards in some sense. Cactus, there is a simplification that you can use, but you don't have to. Almost everybody does. Where you say, I have these source files, compile them in the way that you normally do with the object files, take everything together. That's in make.code.defen, which is in the simplest form just a list of the source code files you want to compile. And also the subdirectories in there, where you can have more source files that are also going to be compiled and things. You have a very large thorn, or you have a third-party library that you can put it in subdirectory. Or I didn't find a little that, for example. I'm not so many other things. Right. So this is what describes the thorn. Cactus then uses a make file, and a typical Cactus directory structure would look something like this, where you have top-level directory called Cactus. Traditionally, the name is really up to you. It's just the directory name. There's the make file. Then you have the arrangement subdirectory. Move to various arrangements. I think here I've only got one. And put in the one for the heat and weight equation that are how to write as one example. And I've left out most of it, just basically ones that I think here. That's the source code. Then there's a second sort of directory hierarchy that starts from the context directory. That's mostly where the output goes. Output and input are strictly separated so that you never have any object files cluttering your source code directory. Everything goes to context, rid of all the object files, because we can just remove the context directory. Sometimes that's the easiest way to wipe everything and a clean start. You actually find there's always a subdirectory. In fact, you have multiple different Cactus builds on the same source code with different options in the same source code tree, just end up in different context directories because they're different options. And for example, you could have one that does binary transfers, one that does binary black holes, or debug and optimize build, whatever you want. That is supported. SymFactory has a default name that it uses sim. If you don't tell it anything, but it doesn't course you do, you could name it whatever you want. In there, if you look at that, then you would find that there is a file called thorn list, which actually happens to be a copy of the thorn list of all the modules that you want to compile, with an actual copy. Then the other files, one of them that will be of interest to us is this file config-info, which is more or less a list of all the compile time options that you gave to the system, more or less. As well as the directory called config data. And instead of that, a file make.config.def. There's a pattern somewhere in here. And these are all the definitions that are actually used. The option list might be a smaller subset of what you want to change. It gets supplemented by default. What's actually then used is what shows up in this particular make.config.def file. Really want to know what's being used, doesn't do want to look at. Then you have a couple more directories. You've got a scratch directory where all the scratch files go, and the build directory where actually object files here init.c.o go. You also find there something that looks like a source code file again, and that's a preprocessed version of your source code after that. And then there's a file that ends in .d that tracks dependencies. Essentially, if you have include files in your source code file, the build system keeps a record of this source file included those header files. So that if the header file changed, it will recompile your source file. The header file doesn't necessarily have just definitions. It could be an actual C source code file or a template source file that you need to recompile. This is in there. Normally, this should mean that if you change a file, you just have make everything files. Can indeed make very confused by changing things outside of its dependency tracking system. For example, if you update your operating system, then some include file in user includers might change. May or may not be tracking here, that things can go wrong. So occasionally you want to clean. All right. Yep.
Do you always build with shared libraries? Also for the static libraries?
We always build static libraries.
Okay.
So the
Repeat question.
oh, sorry. Kat was asking if we always build the shared files or also static files, the static libraries. And the response is basically we are almost always building just the static libraries. Yeah, and we prefer static builds usually on the clusters because it means there's no outside dependencies. Okay. So that's kind of what the structure looks like, and I'll try and explain to you how these files come into being and what they actually. But all of them, I won't go into the CCL files because that's already explained by Soren, but the other things. Right. So we'll do this really all at the very basic level. That I'm not going to use any tools whatsoever. I'm not going to use SimFactory. I'm not going to use get components either. So this is all bare metal. In some sense, how this was done initially, just so that you can see what actually goes on behind the scenes. So this is, you can see there's some cells that you can execute. So the first one here just starts to download a Cactus arrangement. Cactus isn't a single GitHub repository, it's multiple ones that are assembled, usually by the get components tool. But nothing stops you from doing this yourself if you want to. And it helps to see what actually is required. Right, so this first line here, I hope this is readable for people. That basically gets the Cactus repository. It checks it out into the new direction, which I'm calling Cactus Bear. This already is a Cactus one, and I will get it named. Okay. So I should be able to execute that. Hopefully. And running. And what you see beneath this isn't the actual output, it just saves the output that I should get in case anything goes pear-shaped. I would have expected more output, but it's finished. It no longer has a star. And I have a Cactus Bear directory. I suspect this all worked for some funny reason. And I would have expected this output down here, right? Loading Cactus, get the objects, and I'm done. Yeah. Okay. So I have my checked out Cactus. There's nothing in there that I could compile. It would just be the Cactus flash. No thorns here. So I have to to get my thorns separately, this is what get the thorns normally does for me. So I can check and see what I actually have in there. And this minus F option to ls, which you're probably familiar with, just makes ls attach a slash to directories and tries to indicate to me otherwise what type of file I'm looking at without using types. So you can see there isn't a whole lot in there. There's basically copyright, there's a makefile, and then there is the actual Cactus source code in there, and then lib is most utilities that are used by the makers. No thorns, no arrangements, no conflicts, no except, nothing. This is what we have. So not a whole lot. So if I want to get any thorns in there, I have to put in these things by hand. Is anybody following along?
Yeah.
Okay.
Yeah.
And you're about here, or should I go slower? You're good? Okay. So once going to arrangements, there was no arrangements directory. So the first thing that I have to do is make myself an arrangements directory. Then I'm going to change into that. Sorry. Here. There we go. Okay, so in arrangements, I can put in some arrangements with thorns that are useful. I could try and put in the whole TOVs example that we had that's going to be annoying because there's many arrangements that work together. So I picked something simpler. I'm just going to put in there the Cactus wave example array, which is just wave draw examples in C, Fortran, and yeah, C++, I guess. You can see it's the same sort of checkout that I'm using here. Again, Cactus code, Cactus wave, and I'm going to name it Cactus wave, and that's the arrangement. This works because a lot of the repositories that we have in Bitbucket basically are arrangements. It will be the repository, and then there's a subdirectory for Braun, so I can just drop them in there and they look fine. Doesn't always happen. That's why we have the assembly tools. Sometimes there's also things in there that aren't actually thorns. Maybe somebody put in some spreadsheet or so that shouldn't go into arrangements because it's not an actual thorn. So there's a bit of cleanliness that you want. Again, I don't know why I'm not getting any output. This is what I should get. Basically, it just checks out things.
So if we're using external board, that isn't real operations that all the Bitbucket those are.
Yeah.
Is there a specific way we're supposed to do it, or kind of just create something ourselves?
Okay, so the question is what one should do if one has a thorn where the repository isn't in that particular layout and one has just something random. Yeah, you can basically do whatever you want. What I've seen people do is if you have one repository per thorn, you can make an arrangement by make arrangements, make it here for the arrangement itself, and then clone inside of that. You can also put anywhere and make a symbolic link. The repos directory that get components uses is just what it likes. Cactus has no clue about this. It doesn't know that that exists. It only knows about arrangements.
Can I ask about when you ls the Cactus pair? What are those doc, lib, and src directories?
Okay, so the src, the question was, what are the individual doc, lib, and src directories that you see in the Cactus directory when you first clone it? The src directory is the source code of the Cactus / the infrastructure that brings everything together itself. A little bit similar to what src in a thorn would be, but there's subdirectories in there. Lib is all kinds of, it's not actually libraries, it's for the most part Perl scripts and makefile fragments. The makefile that you see is the top level makefile. It then includes other makefile fragments to do things, and some of these are in the lib directory. Doc is actually where the user's guide and the Cactus reference manual live. There's text files in there, and there is a particular makefile target, docs, or make all docs, that compile these to PDF, but the repository also contains a PDF file. And it's the same ones that you would see online when you go to the documentation link on the website. These are the ones that come out of it. And I'll refer to the user's guide in particular. Every once in a while, you'll see that I have links. Details are found in the user's guide. Basically, that's in there. I just link to the HTML version. Okay. More questions, or should I proceed? Okay. So in the meantime, I checked out my Cactus wave. And that alone won't work because it relies on some helper thorns, but it's just physics thorn. It wants some of the infrastructure thorns to actually work. Right? So I'll need some of the Cactus infrastructure. So it's kind of the same game as I had before. I need a couple more. I need the Cactus base thorns, which basically give me the coordinates, hard grids VD. It gives me the boundary conditions, boundary, symmetry, the time thorn that keeps track of what time you are at. Really basic stuff is in there. And that's used by pretty much all the actual thorns, unless I'm making up a deliberately trivial wave type for you, which we have done before. Check this out. Should give me output somewhat similar. I have to do the same thing with what's called an actual driver. I think you all saw Eric Schnetter's presentation about the Carpet X special pilot driver. That's now the new one used for future development in the Einstein toolkit. Hug is 2 generations back. That's the original Unigrid driver hierarchy that used these fisheye coordinates that I think Zach talked about. Has no mesh requirement, is much simpler than Perfect because of that. Works kind of a test case to try things out first. But it's still in there, it's much faster to compile than Perfect. So I'm using that one. But there needs to be something that basically allocates the memory, allocates the grid functions for you, and drives the simulation. That's the drive. And you can swap that out. The hope is that it's more or less a take one out, put another one in, you don't have to change the physics once. Sometimes true, sometimes not.
It wasn't really the test, it was actually the production driver.
Okay. Yeah, and there are simulations with it, right? And the Gordon Bell Prize was one with that thing, I guess.
The modification.
All right, so we need this one as well. You can see it's quick. The monitor terminal produces output like I showed you, apparently not in a juke terminal. And now I would have everything that I would need in principle. These three would let me actually compile the wait for example and run it. If I want to show you something that has to do with external libraries, this is something that a lot of trouble comes and a lot of questions on the mailing list in particular are sourced by external libraries. I want to have one in there. So I'm adding the library that provides access to MPI. Hug would work without MPI, but just so that I have it in there, I'm going to put this in. So the external libraries are basically wrappers that we have Cactus that wrap external functionality into Cactus forms so that they are more easily interfaced. There's ones for MPI that then record, okay, what's the MPI library I have to use? Is it open? Is it open MPI? Is it libmp? Is it something else? We have ones for GSL. We have ones for MREX. These things typically also contain a tar file of the actual library that they can use if there's nothing found on the system. This is a fallback, but it's often useful because you don't need to install so many things in case everything breaks. So I'm going to get the MPI one. It's kind of similar. I need a different arrangement, external libraries, and I need to clone the proper repository in there. Now this is no longer Cactus. This is part of the Einstein toolkit. Has a more lengthy URL. And I'm cheating a little bit. I give the thing an actual subdirection. So there was a question: what do I do if I have a thorn that contains just the thorn itself? The repository is just the thorn. This is such a one, right? So what I'm doing here is I'm creating an arrangement by hand, and I'm cloning directly that thorn. That's one of the things. All right, so I'm going to execute this. Yes.
So if the Cactus can find MPI,
so eBay was asking what Cactus will do if it can find an external, if it can find an MPI in the system, will it still use the external library? Yes, but only as a shim. Right, so the library is the one that searches actually, because each of these libraries can be found in slightly different ways. In principle, you'd hope that something like EKG config will tell you what you need to do, or CMake or something. Fortunately, we are running this on supercomputers, and each cluster decides to do this on their own. They usually have to have a bit of special glue. The libraries have the glue in there, so they will, for example, check is there an MPI CC, particular one. If there is one, it queries MPI CC. What is the library that I link against? What's the header files? And it then uses those. I have an example on it.
I understood Cactus base, you can create functions, Cactus cube, the driver, what is the MPI?
Okay, so the question was that Cactus Base provides kind of basic infrastructure, Cactus Plug provides a driver. What does the MPI want to do? It has no actual code for Cactus in there. It is just there as a vehicle to tell the Cactus build system that MPI exists. The way that these external libraries work, and I'll get to that at the end, is that they can have a configuration script being called by the build system, which is anything you want, a shell script or a Perl script normally, and that Perl script can report back to the build system, set these variables to the compiler, get access to the library and the include files. And all it does is it provides an encapsulation of that script. A lot of these are pretty much empty, other than that script. And our file that we have in case things go sideways and then we build it and we report back, use the one that I've just built. Make sense? Okay, so this, and you see that I'm doing cd dot dot, and I'm back in my original directory this way. And see I'm back in Cactus Bear. I'm back in my main Cactus directory where you would normally run make with any files. Okay, so we have downloaded a very basic Cactus checkout at this point. We have all the source code in place. Now I can start and compile it. So it's makefile based, but I have to give it some options to tell it what compiler to use. I also have to tell it a list of modules, Cactus points to compile in the format. With those, I can in principle go ahead and compile. The Cactus build system it uses make to some degree, in that it doesn't just let you build individual files, but it has a concept of a configuration and then what you want to do with the configuration. So if you check what you can do, then most of what you can actually build isn't a real file, but it might be a configuration name, a sim name that I have. And then you add with a dash what you actually want to do with it. Sim factor, you see nothing of this because it hides most of it, or it's a command line option. But these actually all translate into these pseudo or phony targets to make. The one that's called -config recreates for you a configuration with the options that you give it. And there's a clean one, deletes all the compiled object and library files. Useful, there's one that's called real clean, which deletes everything, including all these dependency tracker files. In case things go really pear-shaped, you're almost at the beginning again. Happens occasionally. And then there's clean deps, deletes only the dependency files. Use if you know what you're doing, or try it if it works, and if it fixes your problem, you're good. If not, run really clean and everything is good. Space saver, time saver occasionally. There's one that is underappreciated maybe, called rebuild. That one is a bit interesting in that mostly what you need it for is reruns these configuration scripts that are in the CCL files. So it will reinterpret the CCL files. It will also then rerun whatever scripts these external libraries use to detect what's on the system. So if you ever have to build an external library that misbehaves, rebuild can help you, even though it's a bit funnily named. I think that's mostly it. One that you will see me use quite a bit here is one that's called build, which doesn't just build everything, but in fact it lets you select what you want to build. It takes an argument, build list, where you can list all the Cactus ones you want to build, and we'll build only those. So if, say, you write your own code, compile it, you get an error, and everything scrolls by because you compiled with J8, tell it to compile only that one thorn, and then more easily debug. Or in my case, I have an easier time walking you through the build process because I know what's going down. And then the last one is called utils, which builds a set of helper tools that Cactus can provide in the thorns. For example, if you're using HJ5, it's these HJ5 slicers from merger utilities that let you slice and dice files. These are small executables that become standalone executables, not the main executable. A little bit similar to apply observers, only that apply observers is much more powerful than anything that these things can do.
Also much more fast.
Yeah. Anyway, so this is the build that you get. Mostly you have to look this up in the user's guide in section B24. There's also a help target, which as far as I can tell doesn't tell you anything else. Right. Any questions on this? This was just a long list of things as a reference. we'll go through the song and dance now. I'm actually creating everything. First thing we'll do is we want a thorn list that lists all the modules that we want to have. If I had to use get components and an existing thorn, then I would have used a thorn list annotation to download. So by doing this, I have to create my thorn list by hand. There are some tools instead of Cactus. You can simplify this one. I'm listing in there. There's one that finds all the thorns that you've checked out, makes a list of all of them, and then there's one called make thorn list that can be used to create a minimal thorn list for only the parameter file that you want to run, so that you don't have to compile everything that you don't need. If you run a simulation with linear JMHD, there's probably no reason to compile GI right there. One is we don't have anything like this. I try to see if I can do all of them. That just basically fails. So that's what I'm doing here is I'm just going to create one by hand. It's fairly minimal. It has the boundaries one in it that gives you the different boundary conditions, Dirichlet, Neumann, whatever else. The coordinates card bit really. There's one coord base that lets you specify your domain a little bit more nicely. The Fortran thorn, which provides some syntactic sugar for Fortran code. IO ASCII and IO basic are basically output thorns that provide ASCII output of various forms. You can get something to the screen. IO digital is a glue thorn that is used by the IO thorns. Only not anything you need to do. Symbase lets you register symmetries, reflection, locating, whatever else. Bookkeeping one, but it's there. Time provides a way of specifying the crawl condition action. That's where you will typically use it. Doesn't do much else for the bookkeeping, but it's. Then there's various plug thorns that are all used by plug the driver, a API reduction interface, a data mover, basically. And then the actual science code. So as you can see, I have 4 science codes in here. I've got initial data from my scalar wave, both as Fortran code and as C code. Then I've got the C evolution code for the wave code and the Fortran evolution code for the wave code. And I've got my external library here. And pretty minimal. Still quite a number, but pretty minimal. Right. Any questions on any of this? Okay. That's one by hand, and I basically created that by seeing what I need to make it fun. Right. That's one. Then the other one that's a little bit more interesting for you probably is the options. That's options to tell the system what compiler to use, what compiler options to use, locations of external libraries, all kinds of things. So everything that's the main contract. There's multiple layers of how this happens in Cactus by now. Cactus itself already has a built-in system to have some knowledge about the operating system that it finds itself on and some knowledge about the compiler that you use. This is called known architecture and exists in here. In lib, maybe known architecture. So lib, that set contains bits and pieces usually for the bits. If you list the content of that directory, and if you list that one, then it'll list you a couple of files, some of which you may recognize as operating systems that you're familiar with. There's Linux, maybe somebody uses OpenBSD. I very much don't think anybody uses Unicos anymore. Solaris is still
10
around.
minutes.
Really?
That's 11:15.
Okay. I'm going to slow it down. Anyway, these are most of them you don't need. The only ones you really care about anymore is Linux and Mac. Darwin, which is the actual name of the operating system. These have defaults in there so that your option list doesn't have to be extremely long. So my option list that I'm going to use, as you can see, is fairly minimal. Basically telling it what's the compilers, and for some oddball reason I have to tell it what NPT is, the preprocessor to use with Fortran files. Should do this automatically, but if I do, it wants to find it in /lib. So it's in there. This is the one that I'm going to use. All right, so this would be this one. And this is one way to specify these options. There's others that you can use. You can also specify these options on the command line to make or as environment variables. Principle, the order is least priority have the environment variables. Next priority has the option list. Highest priority are options that you give on the command line. That's true for the ones that are core Cactus options. It's not true for the ones that you pass to the external libraries with split you out. But these are the three, and I'll probably use some of them. And if you use SimFactor, you actually have used a lot of these, because when we tell people to run SimFactor with verbose, we use option 1 actually. Option 2 is what you mostly use, and option 3 I'll use extensively. All right, so let's run this then. Build our configuration with the make config sub the option. Right? Then it takes an argument options equals where you give it the option file, and an argument thrown list where you give it a thrown list file. And I do not know why one is all lowercase and the other one is all uppercase. This is just how it is. All right, so this ran. I suspect I didn't get any output either. But if I had output, it would have looked something like this. And you've probably all seen all of these. I'm only showing you the beginning where you can see, oh, this is all that's the option list. I'm setting these. I'm getting something on the command line thrown list. And then most of this is then output from configure. Then it said it's going to create a couple of files for you. Already you see the Cactus auto generates a lot of files. And that's basically this.
I ran it, it says configuration weight, it says set up a configuration weight.
Yeah, press enter. Or add this at the end. I wasn't sure whether it would work in the way it worked in mine, but maybe it depends on it. But I think you can just press enter. The new enough Jupyter Lab ones. Does that work? Yeah, okay. So there was a question in the room that it seems to get stuck and asks you, do you want to create such a configuration? There is no none yet. You can press either enter, or if you want to avoid this, you can add that bash trick, type the word yes to the command, then it's happening. And there's other tricks, but the other tricks aren't compiling. Right. So we have one. So this, we have it, we can look at what actually was created. It said it created a configuration called wait for us, which goes to that configs directory that I said exists. Should exist. Type ls. And then do. I can have. Even never ran. Okay. Probably just never ran. Okay, so now it's done. Yes. All right. Let me run this. And now it goes. Okay, so you can see there's a couple of files. Basically, some
5
of those.
minutes, please conclude.
It's true. When I get the 50 minutes questions. Yes. Okay. All right. So you get a couple extra files. Basically, the drones get copied in there. There's this config info file that I mentioned that has the options basically in there. If you actually run this one, yeah, then you see it's basically what I gave plus a couple of headers. You could use that one as an option list if you want it. Useful if you misplaced the original one, you can use this. All right. People still with me? All right. Then what I told you is that this is the short one. The long one is this make config.def, which is everything that's actually used by the build system. can run cat on this. I'll put all of our stuff to screen. And if you scroll down to my prepared output, I think I've tried to give you a bit of an overview of what's the interesting one. And so this is the compilers. It also has the linker, which it uses, and everything else. So if you ever need to know what's actually used, this is the one to check. The idea of giving you a bit of the dirty little secrets that you know where to check for the errors. This is why we ask if you're building anything, give us the config.make directory, because we can see what's in there. Right. So I guess the one that I really want to do, even if we go to the question period here, is I want to do the external library, because this is causing so much trouble. So far we've just made something that configures the core Cactus Flash. Hasn't looked at any thorns yet, but it doesn't even know what the thorns are to some degree. Hasn't even read the CCL file. The options that the external libraries use, which you can also put into the option list, actually parsed at a later stage. They're parsed when the CCL files are interpreted. And the one that matters here is configuration.ccl, which I'm showing you here. You can run this, or you should get the output. That one is actually a short file. And in here, the interesting bit is this line options. That one lists all the options that you can put into the option list that this particular external library, or actually your own one if you care to, could do anything. Anybody could do that. It's just most useful here. Is going to react to. And in here, the list of options that it actually looks for. Okay. So it's MPI options, which you shall not use because you get an error message. Therefore, backup compatibility. Then MPI dir, which is the top level directory for MPI.
2 minutes.
Include directories, lib directories, things like that that you normally see in the options. These are all in there, and you see that there's a last one down here, HWlog dir, which means it actually wants to know if you have HWlog installed, where is that? The MPI library can depend on HWlog, so it wants to know where it is. This may be removed. Yeah.
You say this one can was that binder master line.
So Johnny is asking what I mean by HWlog might be removable. And the answer is yes, in the way that you think, and yes, in the way that I wanted to say. Yes, in the way that Johnny thinks. The configuration.ccl file actually says optional hlog, which means that the MPI library can optionally use HWlog. If it's not there, you can check.
1 minute. Please conclude.
What I meant is I don't think that this particular option is actually required to be present there. I think you can gain access to them. Otherwise, it's too much hassle to remove and maybe something else. In principle, I would guess the only ones listed here should be the ones that this particular library itself controls. Just to have anyway, so and you really only get
30
access.
seconds. Please conclude.
Oh, me, I can't even blame this. You really only get read when you try to compile that one. That's where I'm going to use the build command. I'm saying wait build, but only build the MPI file. Just for kicks and goes. So that means it's now going to actually try and compile it, and we can see what it does. Execute this one. Yeah. Great. You see it says processing CCL file, then it does something, and looks at all the thorns, and then it ends. Again, I've tried to highlight important bits in the markdown one underneath, where okay, so there's person configuration files, and then you will find at the end things where it says running configuration script for thorns. In this case, the Fortran thorn has one, what it does, but there's the one for MPI. And you can see that it then runs and it prints something to screen. It says it found an MPI compiler wrapper and user bin MPI C++. Then it is going to query that MPI C++ for the actual location of the MPI library and anything else that it needs. That's then parsed back to Cactus and actually used. Now, where is it used? Maybe it's not in the options because we didn't put it there. doesn't modify. It also wasn't in make, also is not going to go into make config of that. If that file exists, it actually isn't modifying it. Then it's slightly different location. That's where a lot of the confusion comes from. I'll show you why that is actually not in there. I ls on configs wait, then there is now a new directory called bindings. It actually puts the information in there. The configuration CCL file is to bind together multiple thorns, I guess, or something from there goes in here. So yes.
So in that build command, we were specifically building the API.
Yes.
And then it also built Fortran.
No.
Okay, it says running configuration script.
Yes. Okay.
But I missed how that worked.
Yes. So Deborah's question was, what exactly does the build command do? Because you said build MPI, but it seems to do something for the Fortran thorn as well. And the answer there is that it runs the configuration, parses the CCL files for all the thorns so that it has a consistent view of all the interface files and parameter files that it can, at this point, tell you you're trying to write to a variable GXD in ADM base that doesn't exist. So it parses all of them. It runs all the configuration scripts. And then it tries, once it's done, it tries to compile the actual code in the SRC directory for the thorn that I give it. MPI thorn doesn't have anything in SRC. So nothing gets actually compiled. But it runs the CST part, which is all that I really care about. Okay, so where these actually go is it goes into this rather long path, your configs wait bindings configuration capability. If you type ls in there, you get a whole lot of files, again, shown here in the markdown one. Basically, you get one per thorn. Each thorn could have a capability. And there's two flavors in there. There's definite files, which explains what it provides. And there's depth files that record what it needs. So the puck driver that uses MPI will depend on MPI while MPI provides it. So if you need to actually need to know what the compiler will see, you want to look at the definite file of the capability that you're using. Usually the capability is the thorn name or per case that will be related to that. So let me show you what this looks like, just so that you have seen what it is. And I understand it does not a whole lot of do anything because you're just typing commands, but I hope it gives you a bit of an idea and a ref card later on. If everything goes pear-shaped, what is actually happening? So if I type cat on that particular file, and again, I have it down here, you can see what it says. It sets the MPI here to /user. It sets the group directory to be whatever that is, subdirectory of include with open MPI in the name, and so on and so forth. So this is the one that actually gets passed to the compiler 90% of the time. All right. And can I go 5 more minutes or yes? Sure. Are there lots of questions? Put it this way. Do you want me to continue?
What's next?
We just compile the whole thing. Maybe
That's my question is continue.
so this kind of tells you how all the configuration works. So far, no science code has compiled, right? Nothing. So this now shows you how to get the science code to compile. A little bit what goes on there. So let's actually compile one of my science source codes. The actual science one that I have in there is the wave toy. And I'll start with the wave toy C, and I'm going to use the initial data point for that just because that's easy. Then I use the -build subcommand. I want to know what's going on. I say build with this. If you run this one, it's pretty good. It's quick. There's only 2 source code files in there. Initial data.c, check parameters.c. Then apparently something that you didn't put in here, thorn bindings.c, but that the system auto-generated for you. That essentially calls the internal Cactus routines to register your grid functions both in the flash and your parameters and whatever else. So that all gets auto-generated from the domain-specific language C code that gets compiled here. Doesn't really tell you anything that's going on. It just says compiling. Who knows what this does behind the scenes? And the aim here is to show you what's going on behind the scenes. So I'll have a separate one where I actually ask it, tell me exactly what you're doing. Don't say just compile, but show me every single command line that you do. And for Cactus, this is the verbose option. Here, this one. Okay. So if you pass verbose equals yes to the make system, it will no longer just take compile, it actually shows you every single command line the way that make the deviation date before. I mean, feasible, parallel make messes everything up and do anything wrong. So you can see that I'm passing this as the command line argument, so it overrides whatever verbose option might have been in the option list. And the other thing is that I'm calling touch to make sure it actually compiles the file, because otherwise I just compile it, the file is compiled, and I'm going to do it again. Touching it, making it appear to be newer, then it recompiles. And if you type enter here, this is a whole lot of output, obviously. It's also very long lines, because nobody is supposed to really read this unless you're debugging it. So I won't really point you to anything in here because I think it's counterproductive. Instead, what I've done in the make file, in the markdown down here, is I've taken the interesting two lines and this markdown cell here, I've taken the two interesting lines in the output and I've reformatted them in the way that the human would write them in an actual shell terminal. There's basically two things that are going on. One that says preprocessing and one that says compiling. There's apparently two steps behind that compile step that we were shown. Something is done with my source code before I hit compile. Particularly if you look at this extremely messy line here, in the end you can see it writes to an initial data.c file, same name as the source code file. It's apparently not overwriting my source code file because it's usually there, it's going somewhere else. Then if you look at the next line, what actually gets compiled is that preprocessed file. And you may have seen that, namely if it used an option that's just like the one that I had and you get an error message, it doesn't refer to your actual source code file. It refers to some other file in build. And if you have a clever development environment, it'll happily open that file with the error message in there. Then you fix it and you recompile, and that file gets overwritten because it was preprocessed. This is what happens here, and there is preprocessing going on for both C and Fortran files. For C, it's fairly mild. Basically, the only thing that changes is there is a macro-like thing in Cactus called cctkf name that constructs the name of a Fortran routine that matches a particular C one. Basically, if you're doing Fortran, the old style equivalent of Fortran 9's ISO-C bindings. Pretty much that's the only thing for C. In Fortran, it's much, much more because it actually passes the Fortran code through the C preprocessor. You expand all the macros, all the declare CCTK arguments, all the CCTK arguments, everything gets expanded, which is why you get thousands of lines of code you've never seen before and never want to see again in Fortran files. And that's where this is coming from. So this is what I said first. For C, I think they're actually identical. Have a diff statement in there that says they are identical. And this. You do the same game with Fortran code. True. Fortran code. And I do the diff. You will notice that I have more in here. And I have this in there because it really generates thousands of. Okay, lots of output. Again, in the markdown file, I think I have a more palatable version of it. Basically, what you can see is what used to be a subroutine statement with CCTK arguments. Still is a subroutine statement, obviously, but now all of these arguments are expanded. And because you might have many, many of those, because you might depend on many, many grid functions, many, many points, it gets really long. And the same one afterwards then, where it has to declare the types of all of these solutions. All of these good variants. All right. I also show you the remedy. If you look at any of the files in the sim factory, they better all have the C-line directive equals yes, F-line directive equals yes in there. Because these make Cactus commit code or directives to the preprocessor to tell it which file this actually ought to be, so that the line numbers make sense. Use a debugger, you still end up here, but at least the line numbers of the error messages. That's basically it. Then I'm just going to compile things here once. I take a little bit to compile the executable, and everything that I haven't touched before now gets compiled. And once it's done, you have the main Cactus executable, Cactus underscore wait in the exit direction. What you don't have yet is you don't have any of these utilities that you might be using in Sim Factory. The reason is this is actually separate make term, this minus utils term. Sim Factory just builds them all at the same time. Cactus directly you have to do this by hand. And that's the last line. And I think that's the end of the presentation. Any questions on this? Any more details? All right. Then if there's no question,
I don't actually see any next speaker online.
okay, then I'll make an advertisement. If you actually want to know what you actually want to get exactly what the syllabus said, I would present on. Go to the Einstein Toolkit seminars, einstein-toolkit.org/seminars, and you'll find that there is a seminar called Setting Up Sim Factory on a New Machine. That's been recorded from about 2 years ago, where I have a similar notebook where I explain how to set actually Einstein Toolkit on the Cheyenne cluster that has just been sold by Spitter. And this would be what you would do there. Somewhat similar, I show the steps, I show a difference between individual files. And that probably goes for about 1.5 hours. You have a workshop?
Well, I don't see our next speaker online. I need the link on her. I don't even have her email address. Okay. Good deal. Okay, let's thank Roland again.
So I'm Dr. Victoria Porozova. I did my PhD in Russia, St. Petersburg Polytechnic University. I did postdoc at IMPA. Actually, I'm here right now. And right now I'm working with Federal University of San Carlos. And my position is switched from postdoc to technical leader of quantum project. And I was invited for this workshop. It was an unusual invitation because the idea was try to see how quantum computing could be useful for numerical general relativity. So when I was looking for the connections, I really didn't find much, didn't find at all yet how quantum computing was applied to this area. But my ambitions for this year and the next one is to bring quantum computing for industrial problems and fundamental problems of physics. So here in these presentations, what we're going to do today, the presentation, my talk will be divided into 3 parts. The first part will be about basics, elements of quantum computing. The second part would be about playground with Jupyter Notebook. Also, in a way, simple stuff, especially for all of you who are solving Einstein's equations and so on. And the third part of my talk is going to be about possible insights, how we could connect general relativity for solving nonlinear differential equations with quantum computing algorithms. More precisely, I'll show you some results from a group, how quantum neural networks were applied for some nonlinear differential equations. And yeah, so that's our outline for today. So first, we will start with the history of quantum computing. Now, everybody knows about how Richard Feynman in the 80s offered this proposal about that nature isn't classical. And if you want to simulate nature on a quantum level, the best system to simulate is quantum system, so quantum computer. But not many know that independently also Russian mathematician Yuri Manin in his book Computable and Uncomputable made some notes about limitations of classical algorithms. And he also offered this idea that simulating physical processes as quantum systems, that would be a good idea to use quantum computers for this purpose. And so basically, quantum computing is the intersection between quantum mechanics and computer science and information theory and so on. So quantum mechanics, computer science, they were developing independently. And so until Randall from IBM pointed out that if the computer was made reversible, the heat consumption would be greatly reduced. Well, I didn't go deeply in this topic, but I guess the idea here is about some unitary operations because they're reversible. Then, as we just discussed, was Feynman and Manin, first quantum algorithm, Shor, and so on. Where are we now? Right now, we are in the era of so-called noisy quantum computers. We already have quantum computers from IBM. I don't know, I guess the maximum amount of qubits by IBM, like 400 something. On single atoms, also we use single cold atoms, it's like 1000 something. And D-Wave, they use analog quantum computing, and they actually offered more than 5000 and so on. So for some optimization problems. So basically, by this moment, we already have quantum computers to work with. But they are not perfect. So that's the thing. So some of your quantum algorithms you can run on real quantum computers or on GPUs. So now classical computing. So in classical computing, we have bit and the system would be in defined state, either 0 or 1. And bit will be completely independent one of another. And we have some classical operations, like those are truth tables. You're probably familiar with them because you're computational scientists, researchers. So like I'm a theoretical physicist, I'm not from computer science, so it's not like, you know more about this stuff probably. And those are representation of logical gates in classical computing, where they will perform, the combination of them will perform some arithmetic operations such as addition, subtraction, multiplication, and division. Now let's quickly move to quantum computing. So I was told that the audience knows about quantum mechanics. That's why I didn't discuss quantum mechanics at all here. But when I teach quantum computing, I always start from quantum mechanics because it's just a really logical transition. For instance, here, now we don't work with a bit which will be either in state 1 or 0. We will work with so-called quantum bit, which is called qubit. But qubit is actually nothing more than wave function written in a two-dimensional basis. Because for wave function, you can write this linear combination, because wave function, as you know from quantum mechanics, are based Schrödinger equation, which is linear differential equation, and the solutions of Schrödinger equations, they linear combination of solutions also will be solutions. So this is just the property of differential equation. And from this property, we get the superposition for wave function. And here wave function is written with Dirac notations. And the coefficients before 0 and 1, which we're gonna also define those notations, it's get notations in the next slide. The coefficients are complex functions the square modulus of them represents the probability of the qubit to be measured in a particular state, either 0 or 1. So basically, in quantum case, you do not know in what state your system is, can be prepared in a superposition with the probability distribution. But after the measurement, which you will have to do, you will know the probability of being in one or the other state. So those are just the definitions of, okay, I have a little bit of this. I was checking before. Okay, some spontaneous error occurred. So V represents the states 0 and 1, which actually form bases like this. So this is called ket vector, and it's just a column. And this is also ket vector. If you do complex conjugation and transposition, you will get bra vector. In our Jupyter notebook, we will see both vectors, bra and ket. So in this approach, it's from linear algebra. It was brought by Dirac, and he just invented it. Basically, he brought it to quantum mechanics to simplify some calculations. So in this linear algebraic approach, basically, you just work with matrices. You can represent your wave function or vector state or qubit. As you want to see, you already have synonymous names here in this as this vector. Here you can see the geometric representation of qubit, which I probably don't have time today to discuss, but it's a block sphere. It's an analogy how we represent a complex number on a plane with like the exponential form. So something similar works for a qubit, and so then you can represent it on this block sphere. Most popular libraries for quantum computing are Qiskit and PennyLane. There are other, of course, but these are just the most famous ones. PennyLane, in fact, connected to our group and offered to work together on the course, because we're also developing, and I'm one of co-authors, quantum computing course. It will be called Classical Information and Quantum Information. And we will use PennyLane in this course. So when it will be ready, you can contact to me or give me your contacts. I will contact you back. But for now, for today, we're gonna study with Qiskit. So first, before we start, let's define now the operations which will transform a qubit. So in quantum mechanics, we say we have operators, which are also matrices. Here we use this slang, so-called gates, because before we discussed gates in classical computing. So now we say quantum logical gate. And those matrices are nothing more as Pauli matrices from Dirac equation. So X, Y, Z. I didn't present here Y, but yeah, it's just similar to this. It's just here I, imaginary unit, minus Y. Yeah, and also we have, so those gates, quantum logical gates, are working on single qubit. You can see it by the dimension of this matrix, right? Because if the dimension was 4 times 4, it would work on 2 qubits. Okay, so how Pauli X works? Pauli X acts upon your vector 0, and it flips it. So you just do this multiplication. And the same it does to vector 1. So that's why we call this Pauli X bit flip gate. Also, we can, also this X gate creates rotation of your qubit, like by pi around X axis, and other Pauli gates do the same, but around other X axis. And also we can define, I didn't present here the formula, but you can easily find it. It's a RY, it's also rotational gate. And here you can see on this block sphere, what happens with the qubit. So the qubit just goes from one state to another. Pauli Z. So Pauli Z, you can also multiply, act upon your basis, and you will see that it does nothing to your 0 state, and it gives you a phase, right? Because -1 is the exponential, is the phase. So it will also rotate your qubit if it's qubit in the state 1. So if you apply this to the state psi, then you will, this term will not change, and this term will gain the minus in front of it. Also, by the way, we call 0 and 1 Z bases because those 0 and 1, by the rules of linear algebra, because their eigenvalues after acting with this operator will be +1, -1. And so 0 and 1, they are eigenstates for this operator. So that's why when we work in quantum computing, we say we prepare a quantum circuit in a Z basis or something like that. This Adamar gate. Remember, we discussed superposition. Okay, so if I start, for instance, from 0 state, how can I create superposition? How I can come to 0 + 1? So it turns out you can do it with this Adamar gate. So this is just simple multiplication. I can share the slides after if you want, and you can just repeat all the calculations. Or in fact, all the popular libraries, they also have this part. So right now, we would just do it by hand, but we don't have time. So I'm just presenting it, just walking with you through it. So as you can see, Adamar gate, when it acts upon 0 or 1, it creates this superposition. We call the state plus and minus state. So it's like going to other bases, like we're switching bases here. Okay. Also, we have other important property. It's called entanglement. Entanglement is this property when basically the properties of one qubit are not statistically independent on the properties of other. They are statistically kind of connected. And mathematically, we would say that if the system cannot be separable, presented in a separable way, I mean, wave function, then you will say that the subsystems are entangled inside. And so here you can see the example of entanglement state. It's a Bell state, it's maximal entanglement state. And also, let's consider the operator which will create this entanglement. So it's called C0. And for this operator, the first qubit here is 0. It's called control qubit. The second one is called target. So basically, one qubit is control, one is target, which means what? Depending on the state of your control qubit, the target state will change or will not change. If control qubit in the state 0, then the target one will not change. If it's in the state 1, then it will change. So that's how it acts. Here you see a simple, it's like one of the original algorithms, like Grover algorithms, and how quantum circuit would look like. This is what we will try to do today, but probably not like completely like this circuit. Unfortunately, we don't have time to consider the algorithm, but my idea was to make you interested and to lower the potential threshold for you to start with quantum computing. So today we will start just a little bit of coding, and then you will feel comfortable to proceed on your own. That's the idea. All right. And so, okay, now it's the second part, but I will try to share I will stop sharing because I would need to share Jupyter Notebook. Just a second.
And this notebook should be similar to the quantum.ipynb notebook available on the tutorial server.
Okay. Okay, my Jupyter Notebook is in a different place, but you already have it, right? Let me. Okay, I'm opening. Yeah, Google. Okay, so my Jupyter notebook is being open in the other browser, and I'm trying to see how I can share it. Maybe Steven, for now, not to spend time, can share his screen with Jupyter while I'm trying to put my screen on Jupyter. Because I can share Google Chrome, but I cannot share Bing somehow, and my Jupyter is open in the another browser. Like, mhm. Yes.
I'm sharing it, Victoria.
Okay, thank you
You
so
can
much.
just talk about it.
So, yes, the idea for me was actually to to run in front of you, but okay. I mean, I still have my the idea was to run in front of you and to code it. Maybe still will help you because we actually we prepared, guys. Okay, so we ran all the, and I can just say what we're gonna run, and so Steven is gonna be my hands. So yeah, I don't know why, like I had some problems with Ubuntu and Zoom, so otherwise I would just share from my laptop. Okay, so what we're doing here. So when you have your clean system, right? So first what you do, you install Python, but of course you have Python, and then you install Jupyter, you have installing Qiskit. Then after you installing Qiskit, yeah, we install Qiskit, right? So now we're going to import all the libraries, what we will need. So from Qiskit visualization, we import those libraries, array to LaTeX. We'll need it to represent cat and bra vectors, then state vector, and so on. So just this one, we just copy. Now, we just studied today vectors and direct notations. So guys, check this out. So this is how you will write the cat vector, cat0. So by using two, like the set of two square brackets. Okay, so if we run, I think we should run, right? We should run the cat one. Okay, so Steven, can you scroll a little bit? Okay, so as you can see, after you apply array to LaTeX, you see your column 1, 0. Just I didn't lie, just exactly how we studied before. Now let's do the same with the Hermitian conjugated, how we say, right? It's like transposed and complex conjugated. Okay, so okay. Here, okay, next time. So the idea is that we have to give a student a little bit of like time, but it will be okay. So example 1, create 1 and 1 with Python list. So okay, I think that here we're already demonstrating the with sort of okay. So let's build the same for
sorry, I had my
1
answer.
and cat 1. So let's run it. But it's kind of exercise. But so I want the students to try a little bit here at some point, like maybe not with everything, but because otherwise they will just feel like just a lecture, not a.
Yeah, I'm sorry, I didn't mean to
Okay,
fill
so what
that
are we
in.
doing here? So let's run this. Let's run bra1 and cat1. We should, because we should now to represent, guys, right? We should write array to LaTeX, bra1 and cat1 to represent. So we can add one line after bra1 and cat1, or here, just because it escaped B, right? Like a Jupyter notebook. Oh yeah, here, array to LaTeX, array underline to LaTeX, yeah, and bra0. Bra1, yeah, I'm sorry, bra1, and then after that, cat1. Exactly. Okay, so I think it shows us kind of the first one. Yeah. Uh-huh. Okay, perfect. So now we can see that the bra vector, it should be a row because we did transposition, right? All right, next move to the next one. So how are we going to act with the 0, guys? So what I have 33 minutes. The 33 minutes is, I was told 45 for the talk, 15 for the questions. So I have like 15 something minutes. All right, so how are we gonna write? Write 0. But okay, brace 0, we actually kind of okay, brace 0, it's gonna be 1 and 0, true. Okay, and then we immediately do array to Latia, brace 0, just to display. Nice. Now we should repeat the same for cat, right? So here we did this one, the left one. Together they form bracket. So yeah, now we can copy just bra 0, we can copy the line and just to put, yeah, I'll just write 0 and 1. All right, and array to it. Nice. Okay, so yeah, this is okay. So let's go further to Qiskit state vector class. I guess the idea of this module will be about normalization. So what was some kind of mistake? No, I mean, click nice. Yeah, so Qiskit vector class. So before, when we discussed the vector, the wave function of qubit, we saw, no, we actually didn't see alpha and beta, right? They are complex amplitudes in general, but they also can be sometimes real ones, right? So the idea is that you can use this library, like state vector, for instance, this line, the first line, when you apply state vector to your bra, you'll get this matrix form, right? So it's already different format. And then you can apply draw. Yeah, you can run this line. Yeah, so it actually gives you this beautiful representation as we just saw before. So now let's do the furthest step. Yeah, so what we can do by using state vector, we can create some, this actually, I didn't teach you, but it's a tensor product. When you have 0, 0, it means that you multiply by like a tensor operation to vectors. So you actually expanded your, now you work not in 2-dimensional space, now you work in 4-dimensional space. Like I didn't put the slides about teaching tensor product, but maybe you know. So the idea is that when you have now this already 2-qubit system, right? It's a 2-qubit system, and then we draw by using this draw operation. So now we want to do what? The idea is here to yeah, so let's run this line. It will basically give you this exactly. So now there is an operation if we can check, when we can check that the vector is normalized. So if you apply, now let's try to apply to U, right? Because U is actually normalized. Like we can even do it in the same line if you want, Steve. Just or the next one, yeah. So instead of applying is valid to SV EQ, we can apply to U. Yes, just U and is valid because U. Oh yeah. So guys, the idea is here is that because the coefficients are complex functions and there are probability amplitudes. This okay. So here, no, U is defined. U is defined above, so we can just write U underline. No, U dot. After U, we put dot. Yeah, and then we put is underline valid and brackets. Because we already defined it. Okay, and now we can run. All right. So, okay, no, I'm sorry. It's not you. It's not you because you is a draw one. It's SV underline EQ test, the test one. Okay. When we were doing, yes, test one. Mhm. This one, yeah, as you can see. So I'll explain what it means from physics perspective. So the physical meaning in quantum mechanics only has the probability, and because of that, when you're gonna do integration or summation over the whole space or the whole universe, the probability cannot be more than one. It's normalization. So that's why when you sum the squares modulus of those probability amplitudes, you have to get one. And this is inside of this library, like it's valid, it's inside of Qiskit. So I think your homework here can be like, we don't need to do it now. It's gonna be interesting homework. Create your own valid state vector. So this is, I think Stephen was playing here. Let's check it, by the way. Let's check if it's valid. I feel like, well, yeah, okay, it's gonna be right because it's 9 plus 16, so it's gonna be valid. But what if we put different? Like we can put different and you will see that it will not work, right? It's gonna be false. So your homework, and by the way, Stephen used two-dimensional basis, but you can play even kind of stronger and also use your computational skills. Because once I was teaching a class and one student called it normalization procedure, right? So you can use some like normalize my state, like you can play with this part. Okay, let's go for the next part, Qiskit operator class. So Qiskit operator class is also can be used to represent, yeah, we can just, yeah, here we can just run the lines, I believe. Okay, let's scroll a bit. Yeah. So we should apply different operator class here. I guess it's convenient further on to define gates. Okay, also this part, inner and outer product. I also didn't present on the slide, so I'm sorry, but you know what is inner product from calculus, right? So when you multiply row by column, it's going to be your, yeah. So for instance, if you do, wait a second, okay, okay, go a little bit up. So inner product here in Qiskit is denoted by dot. And so it's dot product. So the output is a scalar. So that's why we get one. But outer product, in fact, it's a projector operator, right? Because we are multiplying what? Column by row. So it will create your matrix. You also can check it by hand. And this is your result. Okay. I believe the next exercise can be homework. Just play with it because you have your notebook saved. So just play and try to display all of this. Let's try to see the next module, simulating measurements using state vector. So we can write state vector, several ones, and then we can display. So we can run this one. All right. Okay. And so, yeah, state vector has this valid class, and also we can display. Now we can play with, I think we need to do this. It only displayed one, right? It displayed because in Python, I don't know. Ah, no, it displayed because it's text. I see. Yeah, of course, no, no problem. Yeah. Okay. So yeah, you can see that one vector is normalized. It's true, and the other vector is not normalized. Yeah. Okay. Simulating measurements is using state vector. Again, let's define V state vector as such, and let's draw it. Okay, so now you can see that amplitude, probability amplitudes can be complex. All right, and what's next? So the important idea here that complex numbers, complex functions, okay, wait. So complex numbers, complex functions cannot be measured by detectors. Like yesterday we talked with the group and like what is photon? It's a click on detector. So photon is more complicated than just click on detector in theory. But the idea is that it's like some say it's a collapse or wave function, but mathematically it's an inner product, right? So you do this dot product, let's say, okay, I will show you later on, but this measure procedure will basically turn your complex amplitudes into real ones. You can see it, right? Okay, so for now we can just see that after measurements, we got the probability of observing a specific state. For instance, here you can see that your state is 0 because in quotes, right? And the probability, can we see if it's below a little bit? Yeah. Yeah, well, you would have to do square modulus of this, 1/2. Particular example vector defined above, the measure method defines the quantum state vector after the measurement. So in order to calculate the probability of your qubits being measured in the state 0, right, you will have to do the square modulus. Okay, let's go below. Let's see some operators. Oh yeah, that's exactly. By the way, try to run it again and you will see that the number on the column will be different. Now it's 5438. So quantum mechanics is probabilistic science, right? And so you will see, yeah, it changed, right? Because it was different, you can see. So it's almost 50-50, then you can observe. When it's 50-50, it means the state is random. When it's in superposition, then it's a random state. You cannot, like, it's not bringing any information. But here, more probability that you will observe your state, your qubit in the state 0. When you're going to build your own quantum circuits to solve your own problems, be it optimization or solving differential equations, you will get like distribution like this. It's not going to be just 2 columns. It's probably going to be several. And you will measure your state. Oh, yeah. Okay, so I see Steven is playing with the count. Yeah, but you can also increase. You can to 10,000. But for 10,000, I think it's also... Yeah, I mean, it's kind of almost equal. But the idea is that when you create a specific algorithm for the solution, right? You will get the higher column for some specific state which you want to find. For instance, it works for time optimization problems like in finance or yeah. But okay, let's go further. Let's go to operator. Scroll a little bit. So by using this class operator, you can act and transform your qubit. For instance, yeah, okay, so we draw and let's try now. So this is, I'm just showing how you can encode the operator, but let's write some kind of simple quantum circuit. Yeah, and okay, let's try to run this one because we can, yeah, we're talking about how sometimes you can visualize, but I think it's already installed. You can visualize. This doesn't work in Python 3.8. Okay, guys, so this is the idea that if you just apply circuit, okay, let me first describe the code, what you see here. From Qiskit, import quantum circuit. After that, you see circuit equals 2, quantum circuit 1. 1 means you have 1 qubit. That's why it's a 42, right? The eternal answer. So you see that it's 1 qubit system, and then you just created it. By default, we always create in a state 0, by the way, in this Z basis. Then you apply Adamar gate, which we studied before. Here they use little h, not capital. And you say, I'm applying to my first qubit. We start counting from 0. So Adamar h, and if it was 2 qubit system, I would put, for instance, 1, it would be second qubit. Then you apply some other gate, like a T gate, Toffoli gate here, like then Adamar and so on and so on. So here I'm just showing how it would, the line from some quantum circuit would look like. Also, let's go down quantum. Yeah, and also for beautiful visualization, you can use this line, but you will have to install or update your Python. Yeah, Qiskit doesn't provide this visualization line, but I found it. Okay, so let's try to do block sphere. Let's see if it works. Okay, so here's what we're doing. I like how fast Steven is. I like how she's helping today. So what we did, so we again applied all the gates, all the Pauli gates, and we printed. We say quantum circuit dot apply the gate, print the result. Okay, let's try. Okay, Adamar. Okay. And the ending of our Jupyter is let's define block sphere. Okay. Return class. Okay. And now you use it. Okay, this is beautiful. So now you use this state vector. Do you see what happened? You started from the state 0. You applied. Can you go a little bit up when we are defining the block sphere? So you can see that in the definition of this function, you in the definition, the only one operation is x, this x gate, and x gate flips. So as you can see visually, now we can go down. On the block sphere, you flipped. So initially you were like here, and then you flip. So you can play with this. You can create your own functions. Also, IBM Quantum, if you register, provides like a kind of playground when you can put gates like this without coding. Oh yeah, so this is why. We can run this one, yeah. Y will supposed to also give this I imaginary unit. So, or maybe, okay, but I actually didn't present how I work. So like, let's go further. Let's go for the Z one. Or it's then. I think it's then, right? Okay, that's it. Okay, so now let's go. Thank you, Stephen, a lot. Now now you guys can create your own Jupyter notebooks or use Penny and so on. But now let me finish the talk with the, I have something in the chat. I'll check really fast. Steve says it's Thursday, so yeah. Okay. Sure. Yeah, now I'm gonna share the presentation again. All right. Okay, so this is the ending of the lecture. So you are solving nonlinear differential equations. So how can we help you? So let's start with not quantum computing or quantum neural networks, how we say, but with classical. So in classical case, you have a neural network, and as an input, you will feed some data. There is a so-called data-driven approach, where you can feed some like vector state, and the output of this neural network will be the approximate solution of differential equation, which is represented here. And the left part, we call it residual, and the neural network basically works by solving and giving you train it, then it will predict you some result and it will give you some approximate solution. So for instance, here, this simplified version of Navier-Stokes equation, it's a Berger equation, we applied quantum neural network here. No, actually, yeah, I think it's a quantum neural network, but now I'm so the idea is here that when you apply a neural network, and this is the approximate solution, so you can interpret it. You see the U is velocity, so you see velocities moving in the with positive and negative components, basically in the velocities. It's like you have parts of the flow with the opposite velocities, right? And when they meet each other, you get in this line, like it's a shock wave. Actually, you can observe it. Like I live in Rio de Janeiro, we have ocean here. And once I observed this shock wave, when two waves, they go and like they meet each other, and then you get this like it's a shock wave. So this is the solution of this, how you can see. Also, we tested this physics-informed neural network for nonlinear Schrödinger equation. It's how mathematicians call it. Physicists call it Gross-Petoyevsky equation for Bose-Einstein condensate. And here we actually compared even their exact solution of this equation. Actually, it's without external fields, so it's kind of simplified version, but it's nonlinear because you can see this term. And you can see that prediction of this physics-informed neural network is quite good for the for it coincides actually. And so I actually believe that these results are from quantum neural networks, but if you're interested in this, you can just email me later on and we can talk, because our group, we actually applied quantum neural networks to solve to solve these differential equations, nonlinear ones. And now in general relativity, when you have this so familiar nonlinear differential equations, what could be potentially done? So there is a famous paper, and actually Lucas shared it with me, and the author is Brazilian. Lucas, I don't know, they are all Brazilians, are not, but Roberta Duarte, we talked about her yesterday, João Paulo sounds Brazilian. So this paper is a pioneering work where classical neural networks were applied for the problems which you probably face in numerical general relativity, right? So was the evolution of dynamics of the gas accreting onto a black hole was considered. It's a very interesting paper. I believe you could try to read it and maybe you'll find it interesting. Why am I showing it? Because quantum computing, quantum neural network, it's like extension. It takes part from classical neural networks. So the idea is that if you can apply quantum neural classical neural networks, you can actually enhance them sometimes with quantum neural networks. So if classical neural networks were applied here, I believe that you can create the architecture of like analogous quantum neural network and test on this problem, for instance. So this is the slide we prepared, which I liked, but I don't know if it's really related to the area. The idea is that that your input would be like a four-dimensional space-time, and then you will get the dynamics as output of the curvature of space-time. But I believe it's not only like basically, you know more what set of problems you solve, right? Like the dynamics of the gas and so on. So, but how it would look in a quantum case. So in quantum case, you have a vector state prepared in like in this tensor product. So here you have 2 qubits, but in fact, better use more qubits because advantage will come with expanding Hilbert space, like 2 to the power of n qubits. And so it could be sometimes that if more qubits in your hands, then you could get some speed up. And so you first do data encoding. You can have classical data, and then you can encode it into a qubit. Like a simple example could be even like 0, 1, 0, 1. You can encode it into qubits by applying those gates. There is also a theorem that any unitary operation, because a gates are unitary, it can be decomposed into a single qubit gates and 2 qubit gates. And this is just an example. So after you apply this block, like a bunch of operators, you will measure the parameters, and those parameters will go to your loss function. So it's like a hybrid, quantum neural network is a hybrid system because it's like a quantum block but connected to a classical neural network. And so then the parameters for optimization, to optimize your loss function, they go inside like theta parameters, and then you apply some methods, gradient descent, classical methods, by the way, we're pretty well developed. And then it's like a loop. And by doing this, you can minimize your loss function, and that would be kind of the algorithm. So we don't know. It's kind of going to be, I guess, your challenge also to think about maybe a collaboration. Maybe we will create something in a group. But we believe that potentially quantum physics informed neural networks can be created for such problems. And here's the algorithm. So on the right side, you see the code written with PennyLane, because PennyLane has more libraries for quantum machine learning. This is the area, it's called quantum machine learning. And this is the kind of simple algorithm. You define encoding, it's a very important part. Then you will define the structure of your quantum circuit, also very important. Then you encode input, then you measure the expectation value. So you measure those probability amplitudes, the distribution. then you calculate loss function, take the gradient, apply gradient descent method for the loss function, and they're gonna update the parameters of the circuit. So this is approximately how this quantum machine learning algorithm looks like. So it's a very interesting area to play with. So I guess my talk is like over. So thank you everybody for attention. And yeah, so this talk is supported by the like foundations NPQ and FAPESP. Also the von Braun Center for Advanced Research and Entropic, it's like a company where we offering quantum solutions for industrial problems, to solve industrial problems, not like, so this is the interest of our group. Yeah, so that's it. Okay. Even like,
Okay, sure. I'm
Sure.
curious. If
do
there's-
I have any questions? Or messages? You can try to ask me some questions. Or share with me if any, at least.
So yes, I have a question. I just typed
Is
it
there
in.
much understanding yet of how to formulate these quantum network problems? Okay, what do I mean much understanding yet? In terms of, like there are several problems actually in all of this. I would, honestly, I want to say something that this is pretty cool what we're doing. We actually, if anybody, one of us decides to actually try to apply quantum computing to numerical general relativity, it's immediately going to be the pioneering work, because I believe nobody yet did it. So by doing this workshop and this talk, we're already sort of creating emerging field, new field. So much understanding about quantum neural networks, well, that's enough. Any guidance, many algorithms I have seen to be unique and bespoke. Look into quantum machine learning. So quantum neural networks, study Penny Lane library, because they are really kind of full of this. Be in touch with the community. You can contact with me or just like, I showed email. So my email is Victoria Porozova. I also do some kind of educational quantum computing, quantum mechanical and theoretical physics on my Instagram. It's exactly the same, Victoria Porzo. So you can contact me the way, yeah, you can find. And because I think in our group, we maybe will try to even also find some quantum neural network for the task. But for us, it would be problematic because we're not specialists in numerical general relativity. So the idea is to define the problem. So you have to first define the problem, and then you have to map it to quantum like solution. And probably it's going to be hybrid. It's going to be AI like methods deployed and so on. And there are some quantum inside. But I think it's very interesting. Whoever writes the first paper is gonna make some noise. Like it's gonna be pioneering. Also, there are quantum schools. So the class enhanced screen doesn't mean they reduce time complexity. I think so. I think so. There are some like always like logarithmic approximations. So the idea is that it should actually enhance exponentially because the power, like the Hilbert space grows exponentially in quantum case, right? Because it's if it's qubit, by the way, it can be qubit, could be even d-dimensional, but for qubit. So it's 2 to the power, okay, 2 to the power n. If n is small, like 2 qubits, 3, 2, 4, and so on, then classical and quantum, they will go like this. But when you grow the amount of qubits, it will go like exponential. You will get the gap between classical and quantum. So far, people didn't get the exponential speed up though. They get only like polynomial, but it's also good. Even if you do some speed up by factor 2 for some industrial problems, it could be like a big deal. You save up a lot of money. for fundamental research, well, I guess so, like in terms of power. I think should be tested, right? So like if you would have to find some physics informed neural network for the problem, for a specific problem you're interested in, then you run. Then you try to create quantum version of your physics informed, and then you do benchmarking. And then you can see if there is a benefit. Like it should be tested. But before I met this group, and we talked with Lucas, and I was more skeptical about quantum neural networks. But in this group where I work now, they're getting like speed up with quantum computing algorithms. Yeah. So there is a potential we should explore. So if we could use kernel, we could use quantum informed, or I think it's called like quantum physics informed, if I'm not mistaken. I don't know, probably like this. But it's already quantum computing, because quantum computing, it's like quantum computing, quantum simulation, quantum machine learning inside. So it's like it's a set, and quantum machine learning or quantum neural networks is a subset inside of it. So yeah. I believe better to start from this side, from like quantum neural networks. So if we could use PIN, then yes, that's my idea. And I asked the colleagues, the experts, they said the same. They have similar idea as I do. It makes sense, right? Because it's like the proposals that are can be it's one of the advantages that quantum computing or quantum networks can sometimes like speed up some already working, but should be done. The work should be done here to check. We don't trust anybody. But in my group where like I worked, they applied quantum computing for like warehouse problem, and now they are we're doing patent on this because we got some speed up for logistics problem, basically for allocation of details of car. So if we can do it with this, I believe we can do. It's just sometimes we don't know how. So okay. Somehow I got on time. So I hope you enjoyed. I guess it was unusual talk for the audience. Thanks. Thank you for the invitation. Should I stay and listen? I think I'll stay, maybe listen to the next talk at least. So thank you so much.
Thank you. Yeah, so it's time for a break. Yeah, well, thank you everyone.
Never work.
It's still.